This is Premier Aerodynamics Podcast number 25, and today we're talking about the aerodynamics of a cricket ball. So, with the straight up, the aerodynamics of a cricket ball, when you bowl a cricket ball, usually there will be some sort of spin if you put some spin onto it and it will swing. And this swing takes advantage of aerodynamics. And to look into this, we're looking at a paper called Investigation of Reverse Swing and Magnus Effect on a Cricket Ball using Particle Image Velocimetry. So, overall, what happens with a cricket ball when you put spin on it? Usually you align at the seam. So a cricket ball has effectively two halves with a seam, outside seam, divided into two along the hemisphere. And when you bowl and you want to put some swing onto the ball, some spin, you align the seam so it's slightly off center. So instead of throwing the ball such that the seam is going head on with the wind, it's actually at an angle. And what that means is one side of the ball is going to have a tripped boundary layer, whereas the other side is not going to have a tripped boundary layer because the other side is going to see a smooth surface, whereas the other side is seeing that seam first. That's going to trip the boundary layer, and then you're going to have a turbulent flow. Having a different type of flow on each side then results in one side separating before the other. And when you have separation on one side before the other, you get an imbalance in the force, and then this causes a swing in the ball. Now, this is a regular conventional swing. Then you get something called a reverse swing. And this is where over the course of a match, so even 20, 30 overs, the ball will start to roughen up. Even if you try to polish it, the ball will still continue to roughen. And what that means is the side that typically didn't transition to turbulent will now start to transition because that surface is rougher. And then that can then create a change in separation, and it might actually separate further downstream than before, and then you get a reverse force, and that causes a reverse swing. So not only does the position of the seam affect the swing of the ball and also the RPM, how quickly you spin it, but also how old the ball is. And this paper goes into that. And this is open access. You can access it with a link below. And let's go through the abstract first to talk about the highlights. So lateral movement from the principal trajectory or swing can be generated on a cricket ball when its seam, which sits proud on the surface, is angled to the flow. So proud means it's just on the top, so it's protruding. The boundary layer on the two hemispheres divided by the seam is governed by the Reynolds number and the surface roughness. The swing is fundamentally caused by the pressure difference associated with asymmetric flow separation. Skillful bowlers impart a small backspin to create a gyroscopic inertia and stabilize the seam position in flight. So what that means is when you're bowling this ball and this seam, you might throw it with a certain alignment, but due to instability, it might change a little bit, so a few degrees here and there, and that will actually stop this swing from happening. At least it will greatly dampen it. So to stop that from happening, they put a bit of a spin on the ball, a backspin, which then keeps the seam of the ball aligned at the same angle throughout the entire flight of the ball. So that maximizes the spin you can get. Moving on, they say under certain flow conditions, the resultant pressure asymmetry can reverse across the hemisphere and a reverse swing will occur. So that was when you have boundary layer, the surface roughness turbulating the boundary layer effectively. Moving on, the results show that a laminar separation bubble forms on the non-seam side, so the one side of the hemisphere, causing the separation angle from the boundary layer to be increased relative to that on the seam side. So the seam side means the side which the seam was on. So you know how I mentioned that they align it so the seam is slightly on one side, so it's not directly head-on with the wind. That's what they mean. For the first time, it is shown that the separation bubble is present even under large rates of backspin, suggesting that this flow feature is present under match conditions. The Magnus Effect on a rotating ball is also demonstrated, with the position of flow separation on the upper retreating side delayed due to the reduced relative speed between the surface and the free stream. So this last sentence is really quite a great succinct sentence explaining what the Magnus Effect is. And I want to talk about this a bit more before we go on because of how succinct it is. It puts this idea very well. I'm going to read it again. It says, the Magnus Effect on a rotating ball is also demonstrated with the position of flow separation on the upper retreating side, delayed due to the reduced relative speed between the surface and the free stream. So the reduced relative speed. And this effectively encapsulates the Magnus Effect in a nutshell. So to talk about this a bit more, to unpack it, let's just consider a rotating cylinder. So not a ball because three-dimensional shape is a bit harder to visualized in two-dimensional. Two-dimensional is very easy. So let's just talk about a cylinder. Imagine a cylinder rotating about its axis, like a typical Magnus Effect experiment. So what is the Magnus Effect and why does this occur? So as the flow goes over a rotating cylinder, let's say the cylinder is rotating such that the top of the cylinder is going with the flow, and the bottom is coming against it. So it has that kind of rotation to it, if you understand that. So what that means is at the top, you're going to have a lower relative velocity of the surface compared to the free stream velocity because it's moving with the flow. So that's going to reduce that relative velocity. Underneath, you get an increased relative velocity because that surface is coming back against the flow. So what this means is the top surface, the flow is going to stay attached longer than over this cylinder than the bottom surface because of this change in relative speed. And this creates a Magnus effect. What this creates is a asymmetric force, and then this creates a force, the Magnus effect. And they're saying the exact same thing happens here with a rotating ball, which it does. So this sentence really sums it up quite nicely. And this is how air affects the flight of a cricket ball. So let's go on and unpack the details more so we can talk about how this happens in detail and all the little things, because it's quite interesting. So first up, they say cricket balls are constructed from a cork center and 4 quadrants of leather tightly stitched around it, forming a primary seam which is proud of the surface by 0.5 to 0.8 millimeters, and 2 internally stitched quarter seams, resulting in a surface that is almost flush. So there's the outside seam, which I mentioned before, making 2 hemispheres of the ball. There also a stitch in another seam in the ball, but that's underneath the surface of the leather. So that's usually going to have a much flusher surface. So on the outside, you really have 2 hemispheres. To extract lateral movement, known as swing, the bowler may angle the primary seam, so the outside seam, to the direction of its initial trajectory. This angle is typically around 15 degrees. So as I mentioned earlier, that the seam is not aligned completely straight with the flow, but to an angle, so 15 degrees about. This creates asymmetry in the separation points of the viscous boundary layers on each hemisphere, either side of the seam, resulting in a lateral aerodynamic force. Now, here's where it gets interesting. There are several manufacturers of top-quality cricket balls, for example, Duke's, Kookaburra, and Sanspareil's Greenlands. I haven't heard of that one, but must be from somewhere else that I haven't seen. Each of which produce a ball with a different design of primary seam, resulting in unique swing characteristics. So depending on what brand of ball you get, you're going to get different aerodynamic characteristics slightly. So one will swing a bit more, as they say here. It is of no coincidence that Duke's balls are renowned for their swing, as it is their design which has the proudest seam, so the one that sticks up the most. There are different surface textures and rates of surface deterioration for balls produced in different colors, red, white, and pink. So that's amazing. Like, you can get different color balls, and that different coloring affects the rate of surface deterioration, which then would affect when the reverse swing comes into play and all that. So such a minor thing that we don't really consider, such as color, does actually have an effect on a cricket ball's aerodynamics. So maybe red does go faster overall, I don't know. And in figure 1 here, so for those of you who are listening to this podcast, figure 1 has a really nice representation of the 2 cricket balls when they have conventional swing and reverse swing. On the one side, they have the cricket ball, they have the exact same orientation, but because for one of the cricket balls, the surface is rougher, you get a reverse swing. But for the conventional swing first, what happens is you have this cricket ball, the seam is aligned about 15 degrees to the free stream velocity. Then the seam side, the turbulent separation, so the boundary layer becomes turbulent and it separates at about 120 degrees from the free stream direction. The non-seam side, the boundary layer stays laminar, and that separates at about 80 degrees from the free stream direction, so much further upstream. And this creates a change in force, a imbalance in the forces, and that creates a swing. Reverse swing, on the other hand, what happens is, so the seam side, you still have a turbulent boundary layer. It's the exact same thing happening effectively. It separates a little bit further upstream at 110 degrees instead of 120, but it's still pretty similar. On the other side, though, where there's no seam, the boundary layer starts off laminar, but then it goes to a laminar separation bubble and then transitions to turbulence and then separates at 135 degrees or even greater from the free stream direction. So laminar separation bubbles are fairly widespread. They occur in a lot of different applications, which is quite funny because in my undergrad, for example, I never really learned about laminar separation bubbles. I never even knew about them. It wasn't until I got to my PhD actually that I found out that they actually existed. And at that time, I was thinking to myself, well, it's a niche, like it's just one of those things. And it influenced my research quite a bit. But again, I thought it was just one of those minor things that you don't really see too often. But there are a lot of applications where laminar separation bubbles do occur, and it's very widespread. And we talk about them at depth in a couple of podcasts, actually. If you want to learn more about it, look at podcast number 11 called NACA 4412 Laminar Separation Bubble, and also look at the podcast we just did, so podcast number 24. Both of those look into laminar separation bubbles a little bit more, and you get a greater appreciation of LSBs. So moving on, they say, of the conditions which are under the control of the bowler and fielding side, swing is principally governed by the Reynolds number and the non-dimensional surface roughness of the ball. There will be little or no swing if the seam wobbles in flight, and consistent pressure asymmetry will not be maintained. So as I mentioned earlier, if you have this seam and you don't put that backspin on there for the gyroscopic stabilization, as they were saying, then the seam will wobble a little bit and you won't get nearly as much swing. To prolong the conventional swing, the bowler and the fielding side will seek to keep one side as smooth as possible by polishing the ball over the course of the innings, and that's true. So over the years, they've changed the rules a little bit in how much you can polish it, how you can polish it, and blah, blah, blah. But often you see a cricketer, they grab the ball and they pretty much rub it on their groin, and that's how they polish it. They seem to enjoy it. And that keeps the ball fairly shiny on one side, which then helps keep this conventional swing happening. But eventually, they say as the ball ages, the surface deteriorates and the reverse swing occurs. Here, the ball will swing in the opposite direction to the conventional swing because it's just roughing out the surface and you're getting a turbulent boundary layer and LSB forming, and then the flow separates at a greater angle of attack further downstream, and then you have a different overall force being occurring. So they talk about the Reynolds number a bit more. They say below a critical Reynolds number of 200,000, i.e. subcritical flow, Achenbach showed that the laminar boundary layer is laminar, the boundary layer is laminar, and the adverse pressure gradient on the sphere causes it to separate at around 80 degrees, as I mentioned earlier, with that figure. Within the critical flow regime, so 200,000 Reynolds number to 400,000 Reynolds number, the boundary layer, 20,000 to 200,000 to 400,000 Reynolds number. The boundary layer transitions to turbulence, and the separation angle is delayed to 120 degrees. So that's that difference, so that creates an imbalance in the forces. As the Reynolds number increases below critical flow, or beyond critical flow, to a supercritical flow regime, the point of boundary layer separation gradually retreats upstream. And they say that the critical Reynolds number reduces as the ball ages due to the increased surface roughness. That makes sense. When it's very nice and shiny, you need to have a high Reynolds number to have a turbulent flow on one side, the non-seam side. But as you increase the surface roughness, that Reynolds number drops, which means that you'll get a reverse swing at a lower Reynolds number. And one point of contention that they had for cricket ball aerodynamics was whether a laminar separation bubble actually occurs on a cricket ball. And to do that, to figure this out, some researchers, they looked into a couple of different methods. They looked at heat flow method, which is where you look at the heating of the ball, and also oil flow fizz. Both of those are really good techniques, and they found that, yeah, they do actually occur. Laminar separation bubbles do occur on the non-seam side, where the surface is smooth, and then you get that transition to turbulence through a not a very abrupt way. So as I mentioned in actually podcast 24, which talks about laminar separation bubbles as well, I was mentioning how the boundary layer can transition through a bunch of different ways, going from not at all to bypass transition, and that it really depends on how great the perturbation in the boundary layer is. Laminar separation bubble sort of is on the more gentle side of the spectrum, as opposed to the bypass, which is like a massive shock to the boundary layer, and it creates turbulence, widespread turbulence very quickly. Back to the paper, they're talking about Magnus Effect. They say the rotation of the ball induces a Magnus force in the vertical axis, orthogonal to the direction of any swing. This deviation from the main trajectory influences the location of where the ball pitches and is also important to the spin bowler. The Magnus force is governed by the Reynolds number and the spin ratio, which describes the ratio of the tangential velocity of the surface of a rotating body to the velocity of the free stream. A typical swing bowler operates at 40 meters per second, with a backspin of about 10 revs per second. This will therefore create a spin ratio of 0.06. Now, interestingly, so this is sort of like the maximum 0.06 spin ratio is sort of the maximum spin ratio that a typical swing bowler will create. So some researchers, they looked at what the effect of spin on a ball does to the lift force, and they found that the lift force measurements on a cricket ball rotating at its axis up to spin ratios of 0.3, so 5 times that of which a typical swing bowler can achieves a lift coefficient of 0.3. So yeah, okay, the spin ratio is much higher than what a typical spin bowler does, but even if the coefficient is 0.05, that's still significant. So it can change the trajectory of the ball still. So you not only have swing, but you have perhaps the ball is being pulled down to the pitch quicker, which means it will bounce earlier. And then when it reaches the ball, by the time it reaches the batter, the batsman, it will probably be higher because it's already bounced a bit higher, depending on obviously where the ball lands in the pitch and all that. But it changes the overall trajectory and the final path. Back to the paper. It has been theorized that if bowlers impart a large enough backspin on the ball, then the Magnus effect is inversed and the pressure asymmetry and wake switch directions. So in other words, if you go fast enough, then the aerodynamics does change. And they go on and say, this inversion effect has been demonstrated computationally and experimentally on smooth rotating surfaces and dimpled golf balls. It is often explained by an effective Reynolds number on the advancing and retreating sides based on the velocity difference. The inverse Magnus effect on a golf ball only occurs when Reynolds numbers are close to the critical regime. For a dimpled golf ball, which has a roughness that is comparable to the seam of a cricket ball, they found that a sufficient backspin causes the effective Reynolds number on the retreating side to reduce to the subcritical regime where laminar separation occurs. So it forces the flow to become laminar instead of being able to transition, and then you get an inverse Magnus effect. So a good cricketer, a good swing bowler, they can really manipulate the ball. So before we go any further, make sure to check out everything we do here at Aerodynamics. Check out the instrumentation we do. We make PIV systems, traverses, and atmosphere hawk. Check out the courses we put on to make you a better aerodynamicist, and check out the International Aerodynamics Conference we put on every year, so aerodynamics can get together and talk about aerodynamics. Back to the paper. So with this paper, they looked at a particular situation for a cricket ball, and they did some experimentation with PIV in that, and they found that there were laminar separation bubbles indeed occurring on cricket balls. So this was one of the big contentions for this paper, and so I was successful in that. One thing that caught my attention though was they said that the free stream turbulence intensity was less than 1%. So that's quite low for a atmospheric condition. I'm not sure what the turbulence intensity is for on a regular cricket pitch, but it's probably going to be more than 1%, particularly on a gusty day. So the free stream turbulence intensity is going to affect the transition. So that's going to affect the critical Reynolds number. It's going to affect laminar separation bubble formation. So that's also going to affect the aerodynamics of a cricket ball. So not only do you have the spin rates and the speeds of the cricket ball, but also the free stream turbulence intensity that the ball is being thrown through. That's going to affect the aerodynamics. So cricket ball aerodynamics is pretty interesting, and they've got a lot of things that can affect how a cricket ball moves, not just the swing, but the Magnus effect, and also all these different parameters that affect these two general aerodynamic features. So that's the end of this podcast. Make sure to like, subscribe. Check out everything we do here at Aerodynamics. Links can be found in the description. And I'll see you in the next podcast. Peace out.